Now for part 9. Alas, we're ready to prove the division property for irrational exponents after a brief walkthrough of continuity and limits. The main idea of the proof we discussed in the previous video, the limit as S sub n for any sequence of rational numbers approaches R for any irrational number of a to s sub n, relies on the fact that f of x equals a to x is continuous for a greater than 0 and x is in the element of real numbers. Then the function we're interested in, for a equals Euler's z, we'll assume it's continuous. But that, ladies and gentlemen, doesn't automatically give the division property of exponents for irrational numbers. The first example is a continuous function. Observe there's no breaks or jumps. We could trace the plot of the function without lifting the drawing instrument. In example 2, the function is not continuous, and the open circles indicate x is undefined at x equals 1. Like we said, we're relying on the exponential function e to x to be continuous for a good reason, because we're taking limits, and those limits have to exist on the graph plot of e to x. So, for a continuous function, the limit of the function as an input approaches a value, say r, is equal to the function evaluated at that value. In notation, for continuity, the yellow box holds. It's applied twice. For continuity, a limit exists if we can approach a value r from the left and right hand sides. For the purpose of this video, that's all we need to cover, because we're assuming e to x is continuous. Because we're taking limits of sequences, the limits need to exist. As such, the yellow box has to hold to develop a proof. Then we can rewrite the yellow box. The orange bullet, we have the limit as Sn approaches r of e to Sn equals f of r. If r equals square root 3, then the limit equals e to x, evaluated at that value. That being said, we'll generously use limit laws in our proof. One is the quotient rule for limits. Essentially, the limit of a quotient of two functions or sequences is the quotient of their limits, provided the limit of the denominator is not 0. That should definitely come in handy. In notation, the limit of f of x over g of x equals the limit of f of x over the limit of g of x. So, the rule allows the division of two limits. Next we have, not surprisingly, the difference rule for limits, which states the limit of a difference between two functions is equal to the difference of their individual limits, provided both limits exist. That's a key phrase. In order for them to exist, e to x needs to be continuous. Basically, if f of x and g of x are two functions, and the limit of f of x as x approaches a is L, and the limit of g of x as x approaches a is m, then the limit of their difference is the following notation. But, with the condition, this rule applies only if the limit of each function exists as a finite number. If we can't meet that condition, ladies and gentlemen, there's no point of going on, but we can. Because we already know an irrational number can be approximated by an infinite number of distinct rational numbers which form a sequence. And, since we're assuming continuity, the limit of this infinite sequence, such as s sub n, is the irrational number itself, which is a single finite value. Very nice. Here's a characteristic that has to do with the current topic of inverse. It has to do with the composite function and seeing it in action. Specifically, the composite rule for limits. If the limit of the inner function g of x as x approaches a is b, and the outer function f is continuous at the value b, then the limit of the composite function f of g of x as x approaches a is f of b. To unpack that, there's two operations happening The first is label 1. We have the limit of g of x equals b. Then label 2. The limit of f of y equals f of b. Then combine everything we just said. The notation is the last orange bullet. Essentially, the rule allows us to take the limit of the inner function and then the limit of the entire composite function as x approaches a equals the function evaluated at the value b. That can help our cause for sure, but we need to consider a variation of that rule which is consistent with what we already said. Here's an example, because it relates to the topic of inverse. If we have f of x equals the square root of x and g of x equals x squared plus 3, to make a composite function, we simply replace the x in f with g of x to get the square root of x squared plus 3. See that? Then apply the composite rule. We have the blue box. We want to find the limit x approaches 1 of the said function. In this problem, to find the limit, we can use direct substitution, so b equals 4. Then we check the function f of x evaluated at the value 4. We get f of 4 equals 2. Since the function is continuous for all x greater than or equal to 0, so it's continuous at x equals 4. We have the last orange bullet. The limit of f of y equals f of 4, which equals 2. Putting it all together, we have the limit as x approaches 1 of f of g of x equals f of b, which just equals 2. The answer to the problem is the double blue box. But if we can't find a variation to the rule, then we are done. But there is, labeled white asterisk. If the limit of the inner function g of x as x approaches a is a, and the outer function f is continuous at a, then the limit of the composite function f of g of x as x approaches a is f of a, provided the limit exists for b equals a and f must be continuous at a. If all the conditions are met, then we have the notation, the last orange bullet. It's the same rule, but here b equals a. Now we have what we need, and it's consistent to what we mentioned already. Let's prove the division property for irrational exponents. Consider the following definition. For a positive base a to x for an irrational number x is defined as the limit of a to q as a sequence of rational numbers q sub n approaches x. What we just said, in notation, we have a to x equals the limit of a to qn, where qn is in the element of rational numbers for capital Q. Next, letting x equal p and r, then we write the following two definitions for irrational exponents, p and r, where the sequences Sn and Tn are in the element of rational numbers. We write them as a quotient to get the equation in the white box. That's what we want to prove. In the first column, we have a to p over a to r, which equals the limit a to Sn over the limit a to Tn. Then we can combine the limits, second orange bullet, making use of the quotient property for limits in its entirety. Second column, how can we rewrite the quotient expression? Red asterisk, we use the division property for rational numbers because the sequences Sn and Tn are defined to be in the element of rational numbers. We needed that limit because, again, we needed to apply the property independently. But we know the limits as Sn approaches p and Tn approaches r. The term Sn minus Tn approaches the term p minus r. Third column, we're using the uniqueness of limits, which means a single convergent sequence has only one limit point. Here, we have two that converge to the said values. However, the difference of the two sequences can be considered as one new sequence, provided they are infinite, which they are, which means we can synchronize them, write both of them in terms of n. Since the conditions are met, we can combine the limits. Voila! The first orange bullet. We get the limit as n approaches infinity of a raised to the power of Sn minus Tn. Nice, because we can apply the composite rule for limits. Next orange bullet. Moving right along, folks. Third bullet. We apply the difference rule for limits, not shown, to make it more easy on the eyes. Essentially, the limit gets distributed to the two sequences. Recall the condition. The rule applies only if the limit of each function exists as a finite number. Since Sn approaches p and Tn approaches r, as n approaches infinity, both sequences return a single finite value. So the condition holds, which returns a raised to the power of p minus r. Therefore, the white box holds. We are done. Very nice.